Okay, I don't think by any means that these insights are unique. They're very obvious, and I'm sure some people use them and have used them. In any case, I kind of came at this independently, motivated by students' inability to understand the ideas of proportionality, their inability to graph, and a number of other factors. But the proportionality thing was perhaps the main motivation in my case. And this is a graphical geometric basis for defining power functions. And a very similar basis can be used for defining exponential functions, so that we develop early the idea that there are different classes of functions that have different types of characteristics. So, working from our usual definition of a power function, that the power function is a function y equals ax to the p, and I don't use function notation here. Here I do the same thing using function notation. I introduce this to students who I don't necessarily expect are comfortable with function notation, and having done this, we get some motivation for function notation. Not something that's handed down in a stone tablet, something that's useful for giving us a more elegant and compact notation for talking about things of this nature. Okay, anyhow, so we start with y equals ax to the p, the usual definition of a power function. If that's the case, then if y2 equals ax2 to the p, y1 equals ax1 to the p, it follows very simply that y2 over y1 is equal to x2 over x1 raised to the p. So then, for example, and the procedure that we're going to use here uses a doubling of the x-coordinate and looks at the result for the y-coordinate. Well, it follows very easily that if x2 over x1 equals 2, then y2 over y1 equals 2 raised to the p. So that doubling x changes y by a factor of 2 to the p. Now we can immediately begin constructing graphs of power functions, and doing this without any need to put values on our x coordinates. In other words, we're going to obtain a general graph for the x to the p power function, which can then be labeled to fit any circumstances, any situation we might encounter where we are using a power function. So, the procedure is just going to be, we start with a series of x values where the x values successively double. Now, one of the easiest ways to create an x scale where you have doubling is to start with a large x value, cut it in half, cut that in half, cut that in half, cut that in half. Then we have y values. Okay, the y values will change by some constant factor, so that this y value is exceeded by this y value by a factor that looks to me to be about 1.3. And this y value increases by another factor of 1.3, this one by a factor of 1.3, whatever the factor is. And I probably didn't line this off really, really well. I wasn't thinking 1.3. I was just kind of visualizing this when I drew these. So this is a hand-sketched, very rough graph. Now, if doubling x changes y by the same factor, then we can simply construct the graph. We take this point and this x value, match it up with this y value, we get a point. Then our second x value with our second y value gives us another point. Third x value with third y value gives us a point. And we end up with a power function. And there's some characteristics of that power function, and they're obvious if we understand the mathematics. If not, well, I'll talk about them in a minute. And we have three cases here. One case where the y factor increases but less than a doubling. Case here where the y factor increases by at least a doubling. Okay? And if, of course, if the y factor doubles, we get a straight line, and that's easy to see. And I'm not going to include that case. So p equals 1, we get a straight line. But the point is, now if we match these values up, we get a graph that's concave upward, whereas for these values here, where the factor was less than 2 but still greater than 1, we have a concave down graph. Okay, and down here we have a graph where the factor is going to be less than 1. And in that case, if the factor is less than 1, of course, we're decreasing the y values. So here the factor, I was kind of thinking 0.7. Okay, this y value is 0.7 of this is 0.7 of this is 0.7 of this. We match this x value with this y value and get a point, this one with this one, this one with this one, this one with this one, this one with this one. And we get a graph that we recognize if we know what we're doing, if we know the mathematics, as a negative power function. Now, matching up the points as indicated, we get these points, this point with this one, this x value with this y value, this with this with this, and so forth. With students, of course, I'll often draw the projection lines. But we get a nice, smooth, concave down curve. And I included the origin in this graph. Let's, and this is also very instructive for students. If we're doubling x as we go this way, then we're going to have x when we go this way, so that we can continue having. We get a point, well, about here. The chalk is getting too wide to draw these points, but we get an infinite number of halvings in here, and we never actually reach 0. And of course, then we can decrease y by an appropriate factor with every interval here, and we again get an infinite series of y values, infinite sequence of y values that approach 0, so that our graph has to approach the point 0, 0, and it makes sense then to talk about limits and to say that, well, 0 is a limit point of this process, so it makes sense to include it on the graph. Similarly here, of course, the same argument leads us to the fact that 0, 0 makes sense on this graph. And then we get to this graph where we're matching up the larger y values with the smaller x values. And we know, of course, that corresponds to a negative value of p. We'll talk about this a little bit when we do the function notation here. And we get a graph that looks like this. And of course, again, we can keep having x as many times as we wish. There's no end to how many times we can cut x in half, but of course, every time x gets cut in half, y increases. Because, of course, y decreases with the doubling of x, y has to increase by a related factor when we decrease the value, when we have the value of x. So if we keep having the value of x, y is going to keep increasing by whatever this factor is. If this is 70%, then this is about 140%. Okay, so we increase y by a factor of about 1.4, and so too, such increases are going to double y, and there's no limit to how many times y doubles, and that gives us a graph that approaches the y-axis as an asymptote, and we do that without ever having to think about the numbers. And one reason this has an advantage is that students don't know how to think about numbers. They've had a calculator in their hand since they were little, and they have never really thought about numbers. They have very little number sense, very little ability to think numerically. They immediately reach for the calculator to multiply 2 by 2. Their automatic reflex when they see a mathematical operation is to reach for a calculator. They never think as a first step. This allows us to talk about the idea of an asymptote in purely geometric terms. Of course, we do need enough number sense to understand a 70% or 140%, and that's something really kind of needs to be established before even approaching this, as I found out recently.